So what we're looking at now is the idea of random samples. So let's start with the definition that a random sample of a population is a group of n values from the population which is equally likely to be chosen as any other group of n values. In other words, the sample that we get is totally random. In other words, it's got just as much chance of being that group of n things as any other group of n things. So, it's often achieved by selecting each of the n values at random. So if I want a random sample of 5 of you, then I just got to make sure that each one I choose to be my 5 is a random selection. So, if I then get a sample, I can do two things to it. I can find the sum of all the values. So, with this one sample, we can then find the sum of all the values. So, say if I'm measuring your heights, then with my sample, I can find the heights of each 5 of you and then add them up. Or, I can find the mean of the values. Which is actually quite similar to the sample. I just add up all the values and divide them by how many I've got. But then instead of just getting one sample and finding its sum or its mean, I can actually get lots of samples from the population. In other words, I can get a sample, find the sum, find the mean, and then do it again. Get another sample, a different sample, find the sum, find the mean. And then do it again. Get a different sample, find the sum, find the mean. And I can go on and on and on and do that lots and lots and lots of times. And so if I repeat this process, I'm going to get a lot of means and a lot of sums. In fact, I could get so many sums and means that I could actually draw a histogram or a column graph of my sums and my means. And I can do that with either a discrete random variable or a continuous random variable. So, if I think about a discrete random variable, rolling a dice. And this is what I've actually done. I've actually done a random number generator between the values of 1 and 6, and I've then graphed the distribution of the values that I get out, and we can see that it's pretty much flat. It's what we'd expect. The probability of getting a 1, so this is the number of times I've got a 1, it's around 1,400. It's pretty similar to the number of times I've got a 6, okay? You might say, well, they're not exactly the same height. There is some random variation, but generally, on the whole, if I do it enough times, I'm going to get a 1 around the same number. I'm going to get around the same number of 1s as 6s and as any other number. So it's just flat. It's a uniform distribution. So I could take a sample of 20 values. These 20 values right here, 2, 5, 5, 3, 5, 2, 4, 5, 6, 1, 3, 5, 5, 3, 1, 4, 4, 6, 2, 3. With these 20 values, we can find the sum and we can find the mean. You've been given those 20 values at the bottom of the page. I want you to find the sum and find the mean. So the sum is 74, and who's done the mean? Marcus, what do you have for the mean? 3.7. Okay. So for this one sample, our sum of all the values is 74, our mean is 3.7. But then what we want to do is we want to consistently repeat this process. So get another sample, find another mean, find another sum. So, in particular in this case though, we're taking samples of 20. So the new sample will have a 20, it'll be a sample of 20, and I can find their sum and their mean. And then as I consistently repeat the process, I'll always be getting samples of 20. That number 20 is very important. And then I can draw a column graph to represent the distribution. Now in this case, the sums and the means will be discrete values. There's only certain values we can get. We can't get all values, so we draw a column graph. So, if I draw a column graph to represent the distribution of sums and means, what do you notice about the shape of that column graph, approximately? What's familiar about that shape? Arif? Looks like a bell curve. And what do we call a bell curve? Okay, so what we can say is we notice that despite the shape of the distribution of x, despite my original distribution looking absolutely flat, then the distribution of sums and the distribution of means are both normally distributed. As for a discrete random variable, so let's try it with a continuous random variable. If I can go back to my rainfall data, I think we can agree that that's not a normal distribution. So let's try taking samples. We're going to do two different sample sizes. We're going to do samples of 5 and samples of 20. Now, for my samples of 5, the sums of all the values is given here, and the means of all the values is given here. For my samples of 20, the sums are given here, and the means are given there. Do those roughly approximate a normal distribution? Yes, they do. I think we can agree that they all roughly represent a normal distribution. But what do you notice about going from here to here and here to here as our sample size increases? So as we go from 5 to 20 and 5 to 20. What happens to the approximation of normality? Marcus, what would you say?
I'd say it's got a much more defined shape.
As we go from 5 to 20?
Yeah.
So the shape gets better defined?
Or like how much it's much easier to recognize as a bell curve, at least from what I'm writing.
Especially in this case, yes, because when we got 5 here, you could argue that that is probably skewed. But as you go to here, it's clearer that this is a normal distribution. So what that actually shows us is that these graphs indicate that the distribution is normal. However, it also suggests that as the sample size increases, then the approximation of a normal distribution actually improves. In other words, it gets more normal. So let's say we're given a question, and this came from a past exam. Given two distributions, or you're told that there are two distributions. One is W, and the other is Sn. Now S represents sum. So it's a sum of a certain number of values from W. So we're taking a sample from the W distribution and finding the sum, and we're doing that lots and lots of times. Now, the histograms are given to us. So we've got a histogram A and a histogram B, and their shapes are roughly given to us. And we're asked, well, which one belongs to which distribution? So which of these is W, and which of these is the sum? What would you say and why? Which one would you say is W, and why? Talk about it on your tables. If random samples of any size is taken from a distribution of any shape, the sums of those samples will be approximately normally distributed. Hence, as A is approximately normal, and B is not, A must be Sn, and B must be W.